We present dynamics-guided diffusion model for robot manipulator design. This is a robot manipulator designed for post-convergence of this target T object. It means no matter how you put down the T, the manipulator is always able to align the T to the same pose after a few squeezing actions without sensors. As you can imagine, this manipulator can be quite useful in assembly lines. When objects are fed in with different poses, we can automatically align them to the same pose. Then the following robot can just blindly manipulate the object. But how can we come up with this robot manipulator design? See, if we're dealing with a different object like a heart shape, the manipulator that can align it should look like this. And 3D objects require specific 3D manipulators to align. How to come up with different designs for different objects? This design process is so counterintuitive. It often takes a very experienced engineer days or months. In this work, we introduce dynamics-guided diffusion model to automate this design process with machine learning. Moreover, we not only generate manipulators that align objects, but also manipulators that can shift objects up, shift them down, right, left, rotate them counterclockwise, and clockwise. The best part is, we generate all of these designs for different objects and different tasks with the same model. How does it work? Here is an object interacting with a manipulator. The object starts with an initial pose. The manipulator closes in around the object, resulting in a delta pose change. And by sampling different initial poses and collecting the corresponding delta poses, we get an interaction profile describing how the object should move after interaction under different initial configurations. Interaction profiles can then be used to construct design objectives. Take convergence as an example. The goal is to reorientate an object to a target orientation, say the target, under any initial orientation. So the object should rotate along positive direction when its initial orientation is smaller than the target, otherwise rotate along negative direction. Then the object's target interaction profile should look like this, with positive delta theta when theta is smaller than theta target, otherwise negative delta theta. Given the target interaction profile and the interaction profile of current fingers, we can easily construct a design objective to update the manipulator geometry. Given the design objective, how can we update finger shapes? In other words, how can we get the gradients of design objective with respect to shape control points? We train a dynamics network to predict interaction profiles in a differentiable manner. The network learns a general model of how a random distribution of fingers interacts with the distribution of objects from simulated interaction data. Then the design objective can be constructed and gradients can be calculated. With the gradients of design objective, how can we efficiently generate good designs? We first train a manipulator shape diffusion model on the uniform distribution of control points. During the reverse denoising process, we use gradients of the objective for guidance. This process is then iteratively performed, and a task-specific manipulator can be generated within 0.8 seconds. What strategies do our automatically generated designs employ to achieve various tasks for various objects? We identify two emergent design patterns for convergence. The first strategy is push and catch, where one finger features a bulge that pushes the object into the hollow cavity of the other finger. Another strategy that the model automatically learns is parallel align. When objects exhibit symmetric flat edges, our designs utilize two parallel surfaces on each finger to align these edges. The shapes designed to perform rotational movements resemble twisted ribbons, curl in a rightward or leftward spiral. For shifting up and down, the generated fingers resemble an hourglass. For shifting down, the shape presents a narrow top that gradually widens towards the base. For lateral movements, the designs exhibit an inward and outward pattern. Our framework also allows designing manipulators for a set of objects to achieve a task. Here is a generated manipulator that can rotate a set of objects clockwise.